Okay, so this video lesson we are looking at the concentration, another quantitative aspect of solutions, the concentration of a solution. Now this, in the note it says that it's a measurement that's similar to solubility. That's correct, okay? Solubility is limited, okay? It can only really describe a saturated solution and even whether something is unsaturated or not, but it doesn't really tell us to what extent it's unsaturated or saturated. Okay, so we can't really compare the solutions. Okay, allows us to describe a solution rather than just use qualitative terms. Okay, and we need this measurement because mixtures can have variable concentrations, not like compounds which have a definite composition. And what that means is salt water, I can mix as much salt in it as I want. But when it comes to salt itself, there's always one sodium and one chlorine. Okay, it's always the same proportion, so it's definite. Same thing with water. If it's water, it's always one oxygen to two hydrogens. Okay, or if you wanted to look at it in terms of masses, you could look at it in terms of masses for water. 2 moles of hydrogen and 1 mole of oxygen translates that to 2 grams of hydrogen and 16 grams of oxygen. That's the definite composition part. Okay, so concentration is a measurement. Okay. And it is a measurement that's close to solubility. It's a ratio, okay? Ratio almost identical to solubility. So this is solubility. So what we're going to do is we're not going to require that the numerator, which is the mass of the solute, to be the maximum amount of solute, okay? And we won't require this to be any specific volume either. We'll just change it to concentration being the amount or the quantity of the solute divided by the quantity of the solution. So there's different ways that we can measure them, okay? And so we'll look at that on the other side of this page. Here's just a little graphic that illustrates what I'm talking about. We got these saturated solutions that have lots of solute in there, and usually to test it out you have to have a little bit of excess solute to know that the solution is saturated. And then we have 2 other qualitative terms, one that's concentrated, so it has a lot of solute in, and one that has only a little, a dilute solution or diluted solution. Okay, and again, these are just qualitative, so we want to change this from qualitative to quantitative by using the formula. Okay, so on the back of the page we have different versions. Okay, I'm just going to go through this briefly. We can have the mass of the solute versus the mass of the solution. Okay, we can have the volume of the solute versus the volume of the solution, and then finally we can have the mass of the solute versus the mass of the solution. Okay, we'll start with these ones a little bit easier. Basically, this ratio just has to have compatible units or identical units in this case. So milliliters to milliliters is good. We could use liters to liters. We could use microliters to microliters. Centimeters cubed to centimeters cubed. Whatever it happens to be, as long as they're the same. Same thing with mass. Okay, mass to mass. Grams to grams, milligrams to milligrams, kilograms to kilograms, etc. Okay. The only one that gets a little bit different is the mass to the volume. So what we're assuming here is that we're dealing with water, and for water, 1 gram is equal to 1 milliliter. So these are the 2 units that are compatible to each other. Okay, so these will be grams to milliliters. Okay, so we don't look at the prefix to be the way that we determine whether it's compatible or not. These have the same prefix, same units. That's because we're measuring the same thing. Here we're measuring water, and 1 milliliter water is really 1 gram. So that's why these end up being compatible. So we don't use milligrams to milliliters. That's not going to be any good. Kilograms to liters, so we just multiply the top by 1,000 and the bottom by 1,000. That one's a good one. But grams to liters is not good. Okay, even though they're both missing prefixes. The last little thing is in order to distinguish these three different concentrations, we usually use these different little descriptors at the end. So this represents weight to weight, volume to volume, or weight to volume. So this one we would write in beside it, weight to weight, or mass to mass. Sometimes we see it that way. This one would be volume to volume, just to be clear about it. And this one would be mass to volume, or weight to volume, whichever happens to be the case. And this is just giving us a little bit more space to talk about how we have a compatible unit. This is the only one we really have to worry about. Okay? Grams to milliliters, because water has a density of 1 gram per milliliter. Okay? And so what we really have here is a mass to mass. A mass to mass concentration. So we use these different units in different ways. Okay, so I've got a couple of examples. Here's one right here. So here's vinegar. It's 5% acetic acid. Okay, so what does that mean? Well, we have a multiplier because a lot of these numbers end up being pretty small. So our multipliers should make sense. Okay, we want to get our numbers to be close to the whole number range. Okay, so technically, if we were to do the calculation, this would have a concentration of 0.05, but because we want this number to be closer to 1, we multiply it by 100 and give it the percent symbol after it. So we've got a percent that we can use. Okay, so we can have a multiplier of 100. It also makes sense to possibly have a multiplier of 1,000. Okay, parts per thousand. So here we're going to multiply by 1,000 to get our value. Okay, to give us PPTs. Excuse me, this shouldn't be there. Or 1,000. Sometimes we see parts per thousand written like that with two circles at the bottom. Okay, ppms, parts per million. And whatever we got from our formula above, that implies that we multiplied by 1,000,000. Or move the decimal place 6 times. Okay, parts per billion, again for very small concentrations. Okay, again we're multiplying by 1,000,000,000. Or moving the decimal place 9 times. Okay? So that's it for the note. We're just going to go through a couple examples just to make sure we're all on the same page and see if we can wrestle out some of these concentrations, these calculations. Okay, so first of all, let's take this next sheet. Okay, so again, what we want to do is identify the important information in the question. Okay. Figure out what our givens are. Okay, maybe use the GREAT method. Given, required, equation, answer, therefore statement. Okay, so let's figure out what our given and our required things are. It's going to be given to us in the equation. So it says a photographic stop solution contains 160 milliliters of pure acetic acid in a 6,000 milliliter solution. What's the volume per volume percentage concentration of acetic acid in the stop bath? Okay, so we have our information. We have 2 bits of key information here. So we've got the 160 milliliters of pure acetic acid and we've got it in a final volume of 600 milliliters of solution. Okay, and that's just right from the question. Basically, what we have to do is figure out where does this go into our formula. So concentration equals solute over the solution. That's all I'm doing. Okay. What's the question that I'm asking? It actually says that there. It says, what's the percentage concentration? So the concentration is what I'm looking for. And I know that this is the question because we've got what in it? And a question mark. Okay? So this is my question. So I'm looking for this. So this is nicely set up already. It has my the question that I'm looking for isolated on one side of the equation, and the other two bits of information are just the ones that I have in the question that I just plug in. Well, which one's which? Well, this actually tells me right here that this is the solution, so I'm going to put that in here. The other thing too is I can tell that this is the solute because it says pure. Okay, if it says the mixture, then it'd say a mixture. Okay, so I just plugged all that stuff in. Okay, and it asks for a percentage concentration, so I'm going to multiply my answer by 100. And when I get to that, the nice thing is the units will cancel, they're compatible. I get a value of 0.267 times 100%, 26.7% volume per volume. Therefore, the concentration is 26.7% volume per volume. Okay? And that's our main way of doing this. All these other ones are slightly different versions of it, so I'm going to let you kind of identify the given information, the required. We're still using the same equation. Okay, we might have to rearrange it a little bit. Okay, in these cases, I don't believe so. But there might be a case where we do have to do that. So go ahead and try this question there on the next example 2. Okay, coming back. We've figured out what the solute in the solution is. It's right in the question. It's asking for a percentage. End up getting a value of 1.12%. Okay. Go ahead and try example number 3. For example number 3, just want to highlight that there are some units that aren't compatible. So we've got milligrams and we've got milliliters. Okay, we need to change one of those. I would suggest you change the milligrams to grams. Those are now compatible. Okay, and then we're going to be able to do the calculation. So go ahead, and it's in parts per billion. Okay, coming back, here we are. We've changed the amount of the solute to grams. These are compatible units, so they cancel out. Okay, multiply it by 1,000,000. I got 8.8 parts per million. If I wanted to change it to parts per billion, I just got to multiply this by another 1,000, and I get parts per billion. Okay, try example 4 on the back. Okay, what volume? Now this one's going to require putting stuff into the formula a little bit differently, so we'll concentrate on that for a few minutes. What volume of 5% solution of sodium chloride can be made using 40 grams of sodium chloride? Okay, go ahead and try that. Write down what's given, required. Start looking at the equation as well. Okay, now we're back. Here's just a different way that you could do it. Solute to solution. I put my concentration in here, and I know I got to change it back to the decimal to get the right formula. Okay, so that's 0.05 by dividing by 100. I don't know what the solution is, so I put an x in there. Okay, then I rearrange the equation. I've got 0.05, and the x was down in the denominator. I multiply it by x to get the numerator, divide by 0.025 to get an 800 milliliter solution. Alternatively, what I could have done is written at this little triangle, so concentration, solute, solution, as a little triangle. And if I wanted the solution, there I would have had my formula. Solute, divide by the solution as a decimal. Have my formula there for me. Okay, try number 5, and that's the end of this lesson.